All right, let's jump right in. We hear the word algorithm thrown around all the time, but what does it actually mean? Today, we're going to pull back the curtain and really understand it. And we'll do it by taking one simple problem and looking at two very, and I mean very different ways to solve it. This is all about the power of a clever idea.
So, what is an algorithm? Honestly, the best way to think about it is just as a recipe. That's it. It's a list of steps you follow to get something done. Doesn't matter if you're baking a cake or launching a satellite, you're following a recipe. An algorithm. A computer program? It's just a recipe written in a language that's super precise so a computer can follow it without getting confused.
But the level of detail in that recipe really matters. For example, if I tell a professional events crew to arrange the chairs, they know what to do. They've done it 100 times. But if I give that same instruction to a bunch of new volunteers, it's way too vague. I'd have to break it down, right? Okay, I need 10 rows and exactly 8 chairs per row. The steps in your recipe completely depend on who or what is going to be following them.
To make this all feel a bit more concrete, let's use a problem that I'm pretty sure we've all run into at some point, probably back in school. The question is, how do you find the greatest common divisor, or GCD, of two numbers?
Just as a quick refresher, in case it's been a while since math class, the GCD is just the biggest number that divides into two other numbers perfectly with no remainder. So for 8 and 12, the biggest number that goes into both is 4. Simple enough? For 18 and 25, well, they don't share any common factors, other than good old number 1. So in that case, the GCD is 1.
Okay, so how would we write a recipe to figure this out? The most obvious way, what you might call the brute force method, is to just follow the definition literally. Step 1, list out every single number that divides into our first number, m. Step 2, do the exact same thing for the second number, n. Step 3, compare the two lists and find the biggest number that shows up on both. It's logical, it makes sense, but you're about to see it's not very clever.
And if we were to translate that recipe into computer code, it might look something like this. You see, we'd need places to store all this information. We'd have a list, fm, for the factors of m, then a second list, fn, for the factors of n, and then, can you believe it, a third list, cf, to hold only the ones they have in common. It's a direct translation of our plan, but wow, that's a lot of bookkeeping.
So we can definitely make this a little bit better. I mean, do we really need to build all those lists? And wait a minute, if we're looking for the greatest common factor, why are we starting our search from 1 and counting up? That feels backwards. A slightly smarter recipe would be to start from the smaller of the two numbers and count down. The very first number we find that divides into both m and n, well, that's it. That's our answer. We can just stop right there.
But, and this is a really big but, here's the catch. Even though our code is a little cleaner and we've ditched the lists, we haven't actually made it fundamentally faster. In the worst-case scenario, say for two large numbers where the GCD is just 1, we still have to check every single number from the minimum all the way down. We haven't come up with a better idea, we've just tidied up a slow one.
For a truly better idea, we have to do a little time traveling. We need to go all the way back to ancient Greece, to a mathematician named Euclid, who came up with what is quite possibly the first and one of the most brilliant algorithms in history for this exact problem.
Euclid's insight was just, well, it was genius. He realized that the GCD of two numbers, m and n, is the exact same as the GCD of the smaller number, n, and the remainder you get when you divide m by n. So instead of counting down 1 by 1, this trick lets you take these huge leaps, shrinking the numbers you're working with dramatically at every single step.
And just look at what that insight does to the code. This is it. This little loop is the whole recipe. It just says, as long as there's a remainder, keep replacing your pair of numbers with the smaller number and the new, even smaller, remainder. The moment the remainder hits 0, boom, you're done. The answer is right there. It's concise, it's elegant, and it is blazingly fast.
So how much faster are we talking about? Let's put some numbers on it. Imagine finding the GCD of two numbers up around 1 billion. Our naive countdown method, that could take up to 1 billion steps. Euclid's algorithm, it would take about 10. No, that's not a typo. Not 10 million, just 10 steps.
The difference is staggering.
And that's not just a small improvement. For a computer, that kind of performance difference is the difference between getting an answer instantly and potentially waiting for weeks, months, or maybe even years for the calculation to finish. This is the true power of algorithmic thinking. So, what's the big takeaway here? First and foremost, a clever idea is always more powerful than raw computing power. You can't just throw a faster computer at a bad algorithm and hope for the best. Second, it shows that programming is a deeply creative field. It's about problem solving, about finding that elegant solution. Because as Euclid proved, the right algorithm can turn what seems like an impossible task into a trivial one. And so often, the most powerful solutions are also the most simple.
And that leaves us with a final thought to chew on. We all have these routines, these little recipes that we follow in our daily lives, from how we organize our email to how we plan our weekend errands. So here's the question. What's one recipe in your life that could use a smarter, more efficient, more Euclidean algorithm?